published on the Southern Ocean. He's very interested in dynamical descriptions of the atmosphere and the ocean. He complained to me that he often applied for jobs, and the oceanographers would say, "You're too much like an atmospheric scientist," and the atmospheric scientists would say, "You're too much like an oceanographer," so he couldn't get a job. So anyway, we took it, so it's not too bad. What else was I going to say? Oh, you'll notice from Navid, you always know when he's in the building because he is the loudest speaker in the building. So there's often a lot of volume coming out of Navid's office, particularly when he's becoming animated about something, and that's just part of it. So we all have grown to love that aspect of Navid. So I think with no further ado, I'm going to hand over to Navid to tell you about ocean eddies and Earth's climate. Over for it, Navid.
Andy, that was delightful. And despite praising on my loudness, I am very disappointed that I didn't win the most loud person in the Christmas RSES party. Somebody else did. I don't know. I have never heard something. But yeah, you've done. You speak.
I was just telling politics from the same part of the walls, so we're all loud.
Yeah, but somehow you managed your way up the committee. Anyway, so I'll be talking about eddies and how they affect the Earth's climate. And what I'm showing you here is a snapshot of the ocean circulation in the North Atlantic. And what you can immediately see is this big basin width feature we call Gulf Stream, like a big current going from Florida or Haiti all up to Europe. But together with this big feature comes all these round eddies, round swirls, we call them eddies, which make the ocean flow look marvelous, but also create a lot of headaches, as I mentioned in my abstract.
Is that a computation or an observation?
This is a model informed with observations. So yeah, so it's so like assimilating as many observations as possible, but it is a solution of the model. Yeah, so it's as I mentioned in my abstract, these eddies are beautiful, of course, but they give us a lot of headaches. And why do they do so? So what I'm showing you here is just a snapshot of how surface currents look. Snapshot from an ocean model, a model we have here in-house. And so you can see if our ocean model has a resolution of the 10th of a degree, this is the grid spacing, the lateral grid spacing of our ocean model, the flow looks more or less like the video. You see big current, you see the East Australian current going down New South Wales, and then you see all the circular features we call eddies. If the resolution is 1 degree, like the one on the left, one would say, what is this? This is a joke. You know, what are you even bothered with this? Despite that, these kind of oceans are the ones that are used in climate predictions and the ones that IPCC reports are based on. So, and the headache comes because one would say, okay, why don't you use this one? It's very expensive to run. This is so expensive to run that if I want to run this for 10 years, there will be a whole Australia-wide meeting to discuss about how much CPU time we're going to spend and whatnot. It's not trivial to run. But so to run this for hundreds of years to get a climate prediction is impossible. So that's why we are running those ones, and we have that kind of ocean. So this is the kind of headaches we have, and keeps us sleepless night. And what I want to give you a perspective, if we were going to go to Museum of Modern Art, this is the kind of art that the IPCC report would be looking at. I mean, it's still beautiful, but a lot of details are gone. So, how do we deal with this? Okay, so that's like the holy grail question: how do we deal with this this distance? So, before going into details and talking about the eddies and the climate, I want to chat a bit about what's the type of general way of addressing problems, the one I am really fond of. So usually I like to think of from a down to up strategies. Start with something very simple, very idealistic, something that might at first not even look like the ocean or the Earth's atmosphere, but something that is very easy to understand. And then, as soon as we understand that, we add more complexity and we move up to this ladder of climate model complexity. So that's usually the path I take. There's the other path, of course, that you start from observations and then you observe everything and then you start to realize which are more important things, and then you narrow down your focus and hopefully some way across this paths meet. So and in general, in climate sciences, we have both top-down approaches, like observations, like if you're observing, via satellites or via research cruises, you are observing the whole, and then you're trying to understand from this whole which are the important physical processes, which are you try to find patterns. We have another method. We can address problems by simulations, and we can simulate big general circulation models, simulate the whole Earth's climate, or simulate simple models. So this approach goes both ways. You can go from simple to more complex, or from complex and then go down to more simple. Or you have also theory. Theory usually means that you start from some laws, some equations of motions, and then you work your way through, you understand what the consequences of those equations are, then try to see if you see these things in your models, then make your equations a bit more complicated, add more details that you are missing, and see where you go. All these things, when they work together, they give us some understanding. And but what I found is very important is this two-way interaction between very simple conceptual models that can be used to inform realistic model development, or in the other way, you're looking carefully on solutions that you get from these models that are very close to reality, and then this can motivate you to think of new conceptual models, new simple conceptual models that will help you build intuition. And I'm borrowing here a nice quote by Isaac Held. He was talking about narrowing the gap between simulation and theory. And, the idea is to narrow the gap between theory and reality. I mean, either realistic simulations or observations. So in what follows, I will try to give you 2 or 3 examples, hopefully 3, if time allows, that will touch on how we go around and try to not have so many headaches. So how we try to understand how eddies work, and then move and incorporate our understanding into the bigger picture and into understanding how these eddies affect the global ocean circulation and the climate. So I'll start from one example. So what you see here is a snapshot of the surface ocean currents of the southern hemisphere. And what pops immediately is this big current that goes around Antarctica. The Southern Ocean, the ocean that is surrounding Antarctica, is the only place in Earth that you can have waters flowing around latitude circles. Everywhere else, there's some continent that obstructs flow from going around the globe. So it's the only place that we can have a current that goes along latitude circles. This is the biggest current in the ocean. It connects all ocean basins. It's very important for setting up for the meridional overturning circulation, for the transfer of heat northwards and polewards, and like in the meridional direction, northwards and southwards. So it's a very important part of the climate system. And the question we're trying to understand is how is this current will respond to winds getting stronger. This current is mainly driven by winds. So if the winds are getting stronger, how will this current change? That's like one question we want to answer. So here's what I was trying to argue before. Indeed, if you see this is one of the main sources of momentum for these currents. Like in the Southern Ocean, there are strong westerly winds that blow more or less along latitude circles in the zonal direction, and these winds are putting momentum into the ocean, into the surface of the ocean via wind stress, and they drive this current. They also drive all these other eddies and whatnot, but these winds drive this current. And what we have been observing during the from the 50s or so, is that these winds are getting stronger. So you see here are various, the bottom panel shows the strength essentially of the winds, and from the 1950s they start getting stronger, and predictions are that they will keep getting stronger. And the winds also start moving south, start moving towards Antarctica. So one question that comes in mind is how will the current respond to this? So if the current is driven by winds, and if I'm making the wind stronger, like my intuition would say the current will go stronger. This is how most people, I think about it. We all think linearly, something drives that, A drives B, A gets double, B will be double. This is linear thinking, and we all hope, I think, that the world is linear and it will be as simple as that. However, it's not. The answer is that it won't behave. So doubling the winds won't double the strength of the Antarctic circumpolar current. And this brings us to this phenomenon we call eddy saturation, and I'll discuss about this in a bit. So what is eddy saturation? Eddy saturation, it's first of all a bad name, but stick with me. This is the name, I didn't pick it, so I don't have it. I won't change it. But it's the phenomenon where the strength of the current becomes insensitive to the strength of the winds. So you're doubling the winds and the current doesn't change. The mean strength of the current doesn't change. So I would say, okay, so where is all this extra momentum from the winds going for? It all goes to eddies. So you're putting more wind in, and instead of the current getting stronger, you have more eddies, more stronger eddies, and more eddies in general. So when you have this sort of flow regime, we call it an eddy saturation. And people have seen this in simple conceptual simulations. So, for example, what I'm showing you here is like results from a simulation from an ocean that looks like this, like a shoebox. And the top part of it, you see this, the black solid lines are boundaries. This is north. This is the Americas. This is Europe and Africa. And here we have the Southern Ocean open and allowing fluid to go from one side to the other. So people have run simulations on this sort of ocean, and they have found the following. When their resolution was very coarse, then indeed, what they're plotting here is the strength of the current versus the strength of the winds. Then indeed, when the simulations had very coarse resolution, 2 degrees, for example, they were doubling the winds and the strength of the current was doubling. So it was intuitive. But when they increased the resolution to certain point when they become like 1/2 or 1/6 of the degree, then they found this new regime when they were changing the winds and the strength of the current wasn't changing. So this is what we refer to as eddy saturation. So when the resolution of your model is high enough, how high, let's not discuss it now, but when it's high enough, you find that the strength of the current remains unchanged, and all this extra momentum you're putting in goes into eddies. So then the question is, okay, well, why is this happening? And the explanation that people have, like the textbook explanation for why this is happening, and I'll try to give it to you now. What I'm plotting here is a section of the Southern Ocean. This is depth, and this is latitude. Think about that you are somewhere in the Southern Ocean, you are crossing a section, something like that. And if you plot the climatology of how surfaces of constant density are in the Southern Ocean, you see that they are sloped like that. They're very sloped, which is very counterintuitive, one would say, because if I go in my bathtub and I create this situation and I let it go, after 1 second it will just all slosh down and the surfaces of constant density will be flat. However, that's not the case in the Southern Ocean, and that's because we live in a rotating frame of reference, and the pressure gradients that are created from these sloping isopyclas are being opposed by Coriolis force, which you can already have in your bathtub. So there is a strong current somewhere here, and this is the Antarctic circumpolar current, and that current creates a Coriolis force that exactly opposes this, the forces from the pressure gradients from this sloped isopyclas. So indeed, this is a situation that could be in equilibrium. Now, these isopyclas, the more they steepen, then the more unstable they become, because the more potential energy they store. So what the winds do, as you increase the strength of the winds at the top of the ocean, it makes these isopyclas steepen more. So if they steepen more, then they become unstable, the whole system becomes unstable, and it produces eddies. And the eddies have the property to make the isopyclas slant back, like unsteep. So people, knowing all this, they were saying, okay, here's the explanation for eddy saturation. You are in a regime exactly where you increase the winds, the isopyclas steepen more, and then more eddies are produced, and then the eddies make the isopyclas come back to their original position. So your mean state, your mean climatology remains the same. Same goes with the strength of the current, but you have more eddies in the flow. So there you go. And that's good. But there's like a key point here. All this explanation requires on density varying with depth. Because if we didn't have that, we couldn't have any isopyclas being sloped on, or sloped more, or potential energy being released, eddies and whatnot. And in technical terms, we call this configuration baroclinic, when you have variations with depth. And also, this explanation doesn't refer doesn't have any reference to the bathymetry, the mountains at the bottom of the ocean. Why am I making that point? Because we also know that the bathymetry is very important. And it was by a seminal paper in 1950s by Walter Mank, who made some back of the envelope calculations and realized that if the ocean, the bottom of the ocean was flat, and given that they knew how much momentum was getting in at the surface, then he predicted that this current must have been 30 times stronger. And since it's not, then a lot of important things has to be happening at the bottom of the ocean because of mountains. And the essence of this process I'm describing, we call topographic form stress. And it's the following. So if you have a very, very simple ocean at rest, this is the simplest ocean we have with a mountain at the bottom. And when you start blowing wind, you will create a current. This is your current, this capital U. And then if you have a mountain at the bottom, you will create also a pressure difference upstream and downstream this mountain. This pressure difference will introduce a force from the ocean to the earth. And from Newton's third law, the earth will push back the ocean. And that pushing back onto the ocean from the solid earth is exactly the force that opposes the current and makes the current not be 30 times stronger, but only as strong as it is. So that was the argument by Moltermann. And we know nowadays from simulations that indeed, if you're running your models and you have a flat ocean, then you won't get something that looks like the flow in the Southern Ocean and has the strength of the Atlantic current. So this process is really important, and this process is not included in the explanation. And another way that the topography is really also very important. Here's some other results from an idealized version of the Southern Ocean. Now, the wind blows out of the page towards you. And these two simulations, one is flat bottom and one has a ridge, a mountain. And you can see the right one with the ridge. The turbulence develops much more quickly. The characteristics of the turbulence are very different. So not only the bathymetry plays a very crucial role in setting up the strength of the current, but it also changes how the whole turbulent flow looks like. So with all this in mind, we want to try to understand how this process comes about. And so the plan is to create a very simple conceptual model that encompasses all these phenomena. And then the hope is that by studying this simple model, we'll understand something more. And so we will take a very, very simple ocean that consists of a number of fluid layers of constant density. Of course, this is an idealization. We'll have some mountains at the bottom of the ocean, and we'll be blowing some wind at the top of the ocean. And this is what I call the spherical cow version of the Southern Ocean. Spherical cow, I don't know if it's very known. It's a joke between physicists that they tend to oversimplify things. So if you ask them a practical question about cows, they come with answers. Yes, if the cow is spherical, we have the answer. So I like the analogy. So this is the spherical cow version of the Southern Ocean. So instead of simulating the whole ocean with the whole complexities and Latin America and Africa and all the sea ice and whatnot, we just will be simulating this sector of the Southern Ocean, and we will be making flow that comes out of here, go back here, it's like a re-enter channel, and this will be our winds, just some steady winds with this structure, more or less like the winds in the atmosphere, but without changing at all, just constant steady winds. And we want to see if this simple model captures the main features of the flow that we want to address. So in more detail, we'll also have some mountains at the bottom of the ocean, very simple mountains, and this is our set. And we will put some Southern Ocean values for the Coriolis parameter, whatnot. And then we can play the following game. We can assume that the density varies with depth with this exponential function, with values very close to the ones in the Southern Ocean. And then we can say, okay, we want to approximate this structure with one fluid layer. Just take the mean of that. Or with two fluid layers, and then each fluid layer has the mean of the density over its depth, or 3 or 4 or whatnot. When we only have one fluid layer, then there's no baroclinic instability, there's no, all this textbook explanation is thrown out of the window. And in that case, we call things barotropic or depth independent. When we have two fluid layers or more, we can have both. We can have dynamics that are depth independent, working together with dynamics that vary with depth. Okay. So, first of all, let's see how the flow looks like. So if we start from rest, this is a case with two fluid layers. We see that after a while, you see a feature that looks like a strong current and a lot of eddies moving around. So, so at least you hope that, okay, I think we get the essence of what we're trying to do here. So this setup includes the physics we're trying to understand. Like we have a current, a strong current, eddies, and we also have good movies, we have good presentation. And so not that the current has this meandering structure. If you squint your eyes a bit, you can see that it goes up and down wherever the ridges are, and this is a known feature of the Southern Ocean circulation, that it follows more or less the bathymetry. So, okay, other than good movies, can we understand something with this model? So we want to play this game now. We will change the strength of the winds and see how the strength of the current changes. Okay. We'll start with one layer, one fluid layer. So there's no baroclinic stability, none of all these textbook things, explanations. So if we start with very, very weak wind stress values, so a realistic value for the Southern Ocean, somewhere in the middle. So if we are blowing the wind very, very subtle, then indeed doubling the winds implies doubling the strength of the current. But when we reach some values close to realistic ones, we see that more or less we can increase the winds by 2 or 3 orders of magnitude, and the strength of the current only increases by a factor of 10. So this is close to what we call Eddy saturation. And then if we overdo it and we go like 100 times the Earth values, we see some other huge transitions. This is the good thing about simple models. You can go all the way, go to town. You can just increase everything, and then you start studying things that you won't see in Earth. And so I won't discuss that. But what I want you to focus is that indeed, when we increase the winds and we reach some realistic values, we see that the strength of the current doesn't grow linearly with the winds. So if we have 2 layers, so we have now the textbook explanation also could be happening even more. The current is even more insensitive to winds. Okay, 3 or 4 layers, essentially no change. So the only step change is when we go from 1 layer to 2 layers. So as soon as we allow some variation with depth, then we see some change. And so we can think of this diagram split in 3 flow regimes. And in regimes 2 and 3, we can have what we say, this is like an Eddy saturated state. Okay, so we want to understand what is happening in those regimes. So if we compare the solutions of the depth-independent cases, the barotropic cases on the left, and the depth-dependent cases on the right, and we measure how much of these eddies we have. This is, like, we can quantify this by this orange curve. We see that indeed, in the depth-independent case, we were finding that the strength of the current was relatively insensitive in this flow regime, where we had eddies. And in the other case, it was more or less insensitive everywhere, but everywhere we had eddies. This is the orange curve. And this gives you a hint of what's been happening. So, but given that we have such a simple model, we can go on and manipulate our equations, and then we can see that the wind stress we are putting on at the surface has to be balanced by something, because otherwise the ocean will accelerate indefinitely. So we see that it has to be balanced either by this process that I was telling you about the flow moving up and down ridges, which we call topographic form stress, or by bottom drag, because the flow touches the bottom and there's some skin friction, some friction at the ocean. And if we look at how much of the wind stress is balanced by topographic form stress and how much by bottom drag, it's always 90% or 80% balanced by topographic form stress, both in depth independent cases and in depth varying cases. So with all this, and like a lot of hitting your head in the wall and stuff like it, we can come up into a new paradigm. And we can see that what we seem to be finding is that downstream of topographic features, eddies appear. It could be because of baroclinic instability or because of other type of instabilities, but there are much more eddies downstream than upstream of topographic features of meridional ridges. These eddies have a signature at the sea surface height, and they create an asymmetric signature because there's an asymmetric amount of eddies upstream and downstream. And this asymmetric signature on the sea surface height has a signature at the bottom of the ocean and creates topographic form stress. So, perhaps this is too much, but the gist of it is that instead of, like, we take a problem, we have an explanation that doesn't seem to be working all the time, and by creating a very simple model, we can generalize this explanation and make it and create a new paradigm. And the new paradigm is that as soon as you have some form of eddies, it doesn't have to be baroclinic instability, as all the textbook might say, you will have this eddy saturation. And like if you want to take one thing out of it, is that these simple conceptual models help you build intuition. So then we can take some intuition we build from these simple models and move on and go to a more realistic problem. How much time do we have? Okay, 20 minutes is good. So the next problem I wanted to discuss is about understanding Earth's interaction. So in climate, the ocean and the atmosphere communicate at the sea surface. So they exchange heat, momentum, everything. And this is an integral part of the climate. So what we want to understand more is this interaction, how the ocean affects back on the atmosphere. Because the usual notion is that the atmosphere affects the ocean. We say the winds drive ocean currents, or the winds set up the circulation. But usually we don't think of much as the ocean affecting back the atmosphere. So we want to probe a bit more on this part of the loop. In particular, we know that the atmosphere will feel the ocean's heat content at the top, so what we call upper layer ocean heat content. And so we're trying to ask, can ocean dynamics create, can the ocean dynamics be important in the feedback from the ocean to the atmosphere? And thus affect the climate, or in other ways, do all these ocean eddies lead to large-scale decadal patterns of variability for the upper ocean heat content, which will have an effect on the atmosphere and thus on the climate? Or, paraphrasing a quote, a popular quote, can an ocean eddy lead to an El Niño? This is an exaggeration, but this is the underlying question we're trying to address. So how do we do that? We have an ocean model at least 3 different resolutions with very different features, as I have discussed, and so we can compare the upper ocean heat content of these 3 models and see if you resolve much more finer scales of motion, do you see different patterns of variability, and thus you can infer that the ocean affects the atmosphere differently. That's one way of doing it. But then there's another caveat here, because all these ocean models are being driven by atmospheric winds and atmospheric reanalysis products of humidity and radiation. And all these products have decadal, vary at decadal timescales. So one would say, yes, you find decadal patterns of variability, but it's because of your force. So to overcome that, we use two different forcings to drive our ocean models. One is the realistic winds from the last 60 years. And the other one, what we call repeat year forcing, is that we take a single year of all of the 60 years, we find the most neutral year, and we force our ocean model with that year over and over and over again. So every 25th of March has the same weather everywhere on the globe. And every 26th, it's very boring, but that's what we do. Okay, and we often try to do this kind of, we're constructing experiments which seem unrealistic, but we're just trying to probe dynamics and to understand more. So yes, this is a very boring weather, but by doing that, if we're forcing with the same year over and over again, and we are looking at patterns that vary at decadal timescales, we are sure that this pattern didn't come directly because of the forcing was varying at that timescale. It came up because something the ocean did intrinsically and created that pattern. So that's how we can be sure that what we see is because it has something to do with ocean dynamics. Okay, so, and what are we going to be looking for? We're going to be looking at the top layer heat content. So we take temperature, the heat of the ocean, and we integrate it over, like, say, the first 50 meters. And then we do a frequency decomposition, and we throw away frequencies that vary less than 18 months. So we don't want to be bothered with the seasonal cycle. And what we are interested in is that patterns that vary at decadal timescales, 5 years, 10 years, 15 years, 20 years. So we take a time series which is like this, which is very dominant by the seasonal cycle. And when we throw away all these frequencies that vary less than 18 months and all frequencies that vary more than 25 years, we get a time series like this. And this is what we're interested in. We want to understand these long-term patterns that vary at timescales of 5 or 10 years. And so we can do this for every latitude, longitude point at the globe, for every model resolution that we have, and for every different forcing that we have, and we can produce like millions of figures. But let's see first how much we go at every latitude, longitude point, and we measure the variance of this orange signal, the signal of the upper ocean heat content that varies at this timescale, decadal timescales. First, for the models that are forced with realistic winds, the last 60 years of winds. And we find this. At first, they might look all the same. And indeed, if you notice at the tropics, they are very much the same. And then when you start looking closely, you can see, for example, in the Southern Ocean, as we increase resolution, there's more variance start appearing, and even more. Or if you go into the North Atlantic, where the beat was at the beginning, things are changing. Or in the North Pacific, again, things are changing. So more resolution, finer scales of motion, you see more variance at decadal timescales. Now we do the same with the boring weather experiments, that we have the same forcing year after year, and we find the following. First, there's nothing happening at the tropics, no variance at the tropics whatsoever. And the mid-latitudes, so the North Pacific, North Atlantic, or the Southern Ocean, the higher the resolution is, the more variance we find. So At the tropics, we know the main modes of climate variability at these time scales is El Niño or La Niña. Now, it's very rainy. And this is a couple ocean atmosphere phenomenon. So if your atmosphere doesn't vary at decadal time scales, which is the case here in this boring weather, same year forcing experiments, you won't find any activities. That's the explanation here. But you see that there's a lot of variance at the mid-latitudes, and the more resolution you have, the more variance you get. And if you plot the ratio of these two variances, you see that at the mid-latitudes, the variance you get from forcing with the same year over and over almost explains 80% of the variance you get from forcing with realistic winds. So, okay, yes, we have more variance as we increase the resolution. What about the patterns? What types of, are the patterns of variability the same between all these resolutions? Remember, we're trying to understand how these patterns or how this upper ocean heat content will affect the atmosphere. So we want to understand if we are modeling our ocean with high resolution, does the atmosphere feel any different? What we find here that it will feel more. Yes, it will feel more, but will it feel any different patterns? So, so that's what I'm trying to sum here. So to do that, we take output from these repeat year forcing experiments, and we do an EOF analysis for the 3 resolutions. And here I show you some examples from the North Pacific, and you see that the model with 1 degree resolution, that model that was almost a joke, but this is what IPCC reports use usually, shows that this is the pattern that will make the atmosphere feel like patterns like that, while the model with very high resolution has a completely different pattern. Not only the patterns are different, but the time scales are much longer. You see that this pattern has a peak around 5 to 7 years, where this pattern has a peak around 20 years. So what we see here is that IPCC reports atmospheres. I'm putting this question here. Like atmospheres usually used for climate predictions feel that kind of patterns from the ocean, while high resolution ocean models give you this kind of patterns. So it's very different, the patterns, very different, the time scales, and one would expect very different the response of the atmosphere to such different nudging from the ocean. So in summing up, so as you have an atmosphere that communicates with a high resolution ocean, then there's much more variance of upper ocean heat content that this atmosphere feels, and very different patterns. So one corollary of this is that the community should move towards doing climate predictions with this kind of models that have high resolution oceans. But that's linking back to this headache problem. We cannot do that. That's also a nice segue for what I want to discuss next. So, at last, I want to discuss a bit of can we, like, since we have this headache and we cannot run this kind of oceans for hundreds and hundreds of years, what we would ideally want to do is to make the cheap 1 degree ocean here incorporate the effect of these small scale features that it cannot resolve, but incorporate it as much as possible. So can we do that? So can we make the 1 degree model feel the effect of the flow features that it's missing without having to simulate it? Okay, in technical terms, this is called a parameterization or an eddy parameterization. We were talking about eddies. So what is the idea underlying here? Is that both of these models say, for the sake of the argument, both of these models solve the same equations of motion, Navier-Stokes equations or whatnot. But because they're solving it on different resolutions, they produce different solutions. So these solutions here they have the subscript 0.10 just to differentiate, and that's the solutions there have the subscript 1. So what we want to do is to find, by some magical way or something, find some forcing that we will add to this model, and we'll make it look as much as possible as the high resolution one. This forcing has to depend only on the flow variables of the model itself. If that's the case, then this is what we call an Eddy parameterization, because knowing the flow from this type of model, we can construct this green term, this forcing term, and we can add as many features of the flow characteristics we're missing. So that's the idea. And there are a lot of this kind of parameterizations that are based on physics or based on physical intuition that has been developed over the years, or based on conceptual models that I was talking you about. There's like very well-known measure-scale Eddy parameterization by Gogh-ian and McWilliams. This is like the most cited paper in oceanography. There's like mixed layer scheme parameterization. There's a bunch of them. And they often work okay, sometimes they don't work. Just for the record, this 1-degree model already includes all of that and still looks like that. If it didn't include anything, it would just blow up and give random numbers. Like it wouldn't even work, I think. Am I right?
In the Southern Ocean.
What?
In the Southern Ocean, it wouldn't work at all.
Okay, so I am right. Let's say I'm right. So it already includes all these things, and it already looks like this blurred version of the ocean. So what can we do about that? Can we make these parameterizations better? That's the question. And what we're thinking of doing is that we want to use all our physical intuition, all the intuition and the physics-based parameterization that have been developed over the years, and also use lots of data that we have. NCI is full of that. Data that come from higher resolution ocean models that include all the physics we're trying to parameterize there, and then develop some physics-aided machine learning parameterization. So the idea is that we will use lots of data from the model that includes the physics we are trying to parameterize, train a neural network, and get a new F that will be even better than before. And the key point here is that also we will incorporate somehow the physical parameters, the physics and the physical parameterizations we already know they work, some conservation laws, some symmetries of the problem. So this is the hard part. That these vague arrows there are probably the hardest part to do. So, but that's the plan. So then as soon as we do that, we take this green term and plug it back into the 1-degree model, and it will look hopefully not like that. That's the hope. So that's work to be done. So you should hold on to your chairs and we'll hopefully hear from me or from somebody else soon. Now let's sum up. What have we discussed today? Or what have I tried to convince you? Is that, first of all, simple conceptual models, even if they look very unrealistic and, at first glance you say, why are you having a square ocean? Why are you having a so simple scenario? They give you intuition and they provide you for new understanding. So they are very useful. Secondly, higher resolution ocean feedbacks onto the atmosphere very differently. Much more variance at decadal timescales and very different hazards of variability. And this may have huge ramifications for decadal climate predictions. It may have a lot of ramifications for predicting and linear predicting the interdecadal Pacific Oscillation or the North Atlantic Oscillation. All these climate modes of variability that vary at time scales of decades or so. and we are trying to understand them using these coarse resolution ocean models as soon as, the hope is that as soon as we somehow incorporate these different patterns of variability that higher resolution oceans do give you, we'll have better predictions and better understanding of those. And as last, what we can learn from that is that the community should move to doing climate predictions with higher oceanic, higher ocean components, or find some better ways to parameterize the things that we cannot include. And with that, I'll stop and take questions. Yes.
You said that see they use the 1-degree models.
Yeah.
Will the conclusions and recommendations change if they use the better ones? Or you don't know yet?
I don't know, because there are very, very little coupled climate models that have been done with. I mean, there are some coupled climate models that are included in the CMIP collection of climate models that have been done with higher resolution oceans, and that yes, they show different features. They show different, predictions in some respects, but I cannot really answer that. I don't really know. I'm sure they will, because that's what all the research is showing us, not just my research, like results from all over the community. But the problem is that we cannot do it. So yeah, yes, I think 1 or 2 laboratories in the world have managed to run like a 200-year predictions with a 10th degree resolution, but that's about it.
So we do have a question online. I'm going to see if Merrily can say something.
Okay, can you hear me?
Very well.
Ah, excellent. Thanks, Navid. That was a fabulous talk. The question I had was, it's really fascinating to see the effect of ocean resolution on decadal variability in the climate system. And we've long had an issue in comparing paleoclimate reconstructions with models, in that the paleoclimate data always tend to show more variance in the decadal and longer timescales than in the models. And so is this potentially something that could resolve that issue that we've been seeing?
That's what I think, yes. I mean, perhaps we should discuss more in detail about the issue that you've seen, but yeah, I mean, the results I've been showing, or do show that, when you have an ocean with much higher resolution, you get more variance at decadal timescales, and also the signal goes to having a peak at longer timescales, and the patterns are different. So perhaps that is. So when you're saying you're comparing with what usually? Coupled 1-degree models?
Yeah, well, just generally with CMIP scale models, and comparing with paleoclimate data. And I guess one of the thoughts has been, do the paleoclimate data somehow sort of redden the signal, or emphasize that longer term variability in the way that they're preserving the climate system. But I guess this is another avenue to look at as to where that difference comes from.
Well, in CMIP 6, I think there is 1 or 2 models that have a higher resolution ocean. So perhaps I would suggest comparing your paleo data with that model only, and then compared to the others, perhaps you could get a hint of if that will be the answer to your question. But yeah, I would say, if I had to bet, I would say yes. But yeah, I don't know.
Very interesting. Thank you.
Can you do one more question online?
Yeah.
Paul, if you can unmute, then go ahead.
Hi, thanks for a great seminar as well. I really liked it. Some question about example 2 though.
Yes.
Your experiments showed that if you force the ocean with an atmosphere, you get more decadal variability at higher resolution, right?
Yes.
But I thought the goal was to show that this very higher variability in the ocean, how much that mattered to the atmosphere. And I guess I didn't really see
Yes.
Sure that this decadal variability in the ocean will really matter to the atmosphere and how much it will matter?
Okay. Yeah. Indeed, I haven't touched on that, but let me add 2 points on that. First of all, you're already touching next research questions we're trying to answer. So that's like you're on the right track. I mean, the first question indeed is that, oh, this variance, is it, how much does it affect? Like, is it a lot or is it little? You don't have a way to quantify. So if we can compare the variance of sea surface height, which is sea surface height is sort of a prop for the same thing for upper ocean heat content, and that even in the repeat year forcing experiment, we can see similar type of variance with comparing to altimetry, for example. So at least we know that the variance we get, it's not minute. I don't know if that touches on the first part of your question.
I'm still just listening. It's okay.
So that's one part, but to really answer your question, what we need to do is to do couple climate model experiments, and that's what we're on, like what we're doing now. Try to, like now, educated by this, try to do some couple climate model experiments and see indeed if this difference in patterns and time scales has an effect on the, you know, overall. So you have to wait a bit more on that.
I guess I'm asking what maybe what your intuition would be. Like my intuition is that the atmosphere, I don't know how much it would care about decadal variability in the ocean. I feel like it's faster.
Oh, okay. What do you mean it's faster?
Well, I feel like
the atmosphere is faster.
Yeah, the atmosphere is so much faster there, you know?
Okay, so, okay, my intuition, perhaps, I'm not really, I don't know how much I would bet on that, but if, for example, the interdecadal Pacific oscillation is some sort of resonance mode that occurs, and if you have the ocean nudging the atmosphere at the right frequency and with the right pattern, perhaps you will excite that mode. So that's kind of the underlying hypothesis we have. Like perhaps the 1 degree ocean does not provide the proper nudging or the proper nudging to the atmosphere, and that's why when you do climate models with 1 degree ocean, you don't see as many or as strong interdecadal Pacific oscillation as you would see when you put the right pattern in there. So that's where we're going. But yeah, it's a hypothesis still.
Thank you.
Okay, there's a couple more questions coming from online, and there may be some more in the room. But what I was going to say is it's 2 o'clock, so maybe what we should do is say thank you once again and move to a more informal discussion, which you can continue on Zoom and ask questions.
Yeah,
okay?
sure.
So some of us have to disappear for 2 o'clock appointments.
Yeah.
So thank you very much again, Navid. We'll keep the Zoom running as long as Navid has patience.
Yeah, I have a lot of infinite patience.
So,